Hello, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics. Today I'm going to be helping you through some high school level and college level chemistry problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tuition. Okay, let's get into it. So for our first question, we would like to find out the Lewis structure of methanol. So from its name, we know, of course, it's an alcohol, organic chemistry. So we have, let's first find out our valence electrons. And we know that we have 4 from carbon, if there's just 1, plus 1 from hydrogen, but then there are 4, plus 6 from oxygen, which is 1. And this would give us 14 valence electrons. We can additionally check its index of hydrogen deficiency, which would be 2 times the carbon, so there's 1 carbon, plus 2 minus 4 for the hydrogens, and then there's no nitrogen, and there's additionally no halogens, over 2. This is going to give us 2 plus 2 minus 4, which is equal to 0, which means the single carbon is saturated in hydrogen, so you're not going to see any double bonds or anything like that. Let's just write that all out. So we know that that is correct so far. The bonds that are linked to hydrogen can only be 1. So let's find out where the rest of these valence electrons go. So we have 2, 4, 6, 8, 10, and we remain with 4. Oxygen's already made its optimized 2 bonds, so we can just place those extra 2 valence electrons on the oxygen, and that becomes our final answer. Okay, next we'll be looking for the Lewis structure for a couple of molecules. Let's start up with this. And so we know, let's first count the valence electrons as usual. And we know that from Si we get 4, and from chlorine we get 7, but then there are 4 of them. So this gives us a total of 28 plus 4, which is 32 valence electrons. We know chlorine is optimized to make 1 bond. So let's have Si as the central. Let's additionally add those valence electrons, the extra ones. And let's see if we have anything left over. 2, 4, 6, 8, 10, 12, 13, 16, 18, 20, 22, 24, 26, 28, 30, 32. So no extra electrons left over, and everyone is satisfied here with no net charge. So that is our final answer for that. For our next one, we will be doing SeCl2. Again, let's count the valence electrons. Se has 6, Cl has 7, but then there are 2. So 14 plus 6, and that's going to give us 20. So let's of course put Se in the middle. Add on any valence electrons that we can that are remaining. See if we have anything left over. So 2, 4, 6, 8, 10, 12, 14. Sorry, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And this becomes our final answer. Next on, move on to the next one. And we have COF2 with C as our central atom. Let's count our valence electrons again. And let's just note this is optimized to make 4 bonds, optimized for 2 bonds, optimized for 1 bond each. Our valence electrons are going to be 4 from carbon, 6 from oxygen, and 2 by 7 from fluorine. And that's going to give us 14 plus 6, 20, plus 4, 24. So you have 24 valence electrons to figure out where they fit. Let's just start with this general map. Okay, now we know oxygen is optimized for 2, and carbon is optimized for 4, and F is optimized for 1. The F have been optimized, as we can see, but carbon is still missing 1, and oxygen is missing 1 too. So the best answer here is to, of course, put a double bond right there. And then let's put around the valence electrons. The remaining valence electrons. Okay, and let's see if we have anything left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So everything has been organized. And that's going to be our final answer for that one. Okay. Now, next up, we want to answer the question of what is the bond order of molecular oxygen. So the bond order is something that we deduce from the molecular orbital diagram. And the equation is the number of bonding electrons minus the number of antibonding electrons all over 2. And the bond order is very, very useful for giving us chemical properties that can't necessarily, so the molecular orbital diagram is useful for calculating things like the bond order that would give us properties that we can't directly calculate, like the bond length, the bond strength / energy, and the magnetic properties. And so now we need to figure out how to draw the molecular orbital diagram of oxygen. So the molecular orbital diagram is generated by the combining of atomic orbitals. And so we have 2 types of combinations. We have constructive, which means you combine them when they're both in phase. And this is what makes our bonding molecular orbitals. And so this will form something like this, where you have a bit more density than before in between the 2 atoms. And that is what our bond is. Or we could have destructive addition, which is when you add them when they're out of phase. And what this does is it reduces the density, probability density between the 2 of them. And this is what gives us, this is bonding. And this one is anti-bonding. So additionally, because we have different types of atomic orbitals, we have different combinations with them. The general rule is that in order for them to successfully combine, they need to be similar in energy and symmetry. What this means is only atomic orbitals of the same level can combine into a molecular orbital, which means you can only get 2p combining with 2p, or so 2p combining with 2p, or 2s combining with 2s to form whatever it is. So because S is quite simple, you will only have the sigma bonding and the sigma antibonding, and this is just a general notation. And for P, we will have, again, 2 types of combinations. So we still have the bonding and antibonding, but they can combine in different ways because of the shape of the p orbital. So if we just draw out the shape of the p orbital, we know that we have 3. And so we have the on axis, and on axis will be the axis of combination. And so that would typically be the z-axis, and depending on the sign is when you'll get bonding or antibonding. So for example, these two are in phase, and so you'd get something that looks like that, looks like that. And you can of course have out of phase additionally, but because of the remaining, two p orbitals that are off axis, so let's have something like this, and then you get antibonding, which would look something along the lines of that. And let's just have blue for our positive and red for our negative, and it would look something like that. And then again, also symmetry is very important when it comes to molecules. You would have different labels depending on the symmetry about the inversion axis. And so you have Gerard and ungerard, which are again just symmetry labels. These are important in cases like this where you have the same atoms combining, where symmetry is possible. And so Gerard means that the sign remains upon inversion. So like in this case, in the case of, so in this case, we would have Gerard. And in this case, it doesn't remain the same, it would flip, so it's ingerard. And so for the out of plane ones, we're gonna name them pi orbitals instead. So we'd have the y-axis and the z-axis, and both of them, of course, would also have their bonding and antibonding. So this is where the different levels of the molecular orbital diagram come from, because antibonding orbitals tend to have higher energy than bonding. Because of this out of phase relationship, there's going to be an increased repulsion here, and that's going to increase its energy. And that's about it. I'm just explaining the general things that you'll see in the molecular orbital diagram. So let's get to drawing it. So generally, energy will be going that way. Let's first draw out the atomic orbitals. We have O and O, and we're going to have O2 right here in the middle. So we have the typical 1s, and we're going to have a 1s antibonding and 1s bonding. Sorry, just draw those in red after. For the antibonding, bonding, we have 2s. And remember, because they're s, we're only going to get 2 because we don't have anything that's out of plane. It's simply a spherical shape. And then lastly, we have the 2p. And this is where we get the out of plane combinations. And so we're going to have 2 here, and 1, and 2. Let's label them. Let's label the molecular ones too. So this is going to be our sigma for 1s, our antibonding sigma for 1s, our sigma for 2s, our antibonding sigma for 2s. The antibonding is just notated with that star. Next up, we have the pi 2p. So this is going to be the 2 off-axis ones that you see in the x and y planes. And then we have our sigma 2p. This is going to be the on-axis one in the z plane. Next, we have our pi 2p but antibonding and our sigma 2p but antibonding. And now we fill in the electrons. So we know oxygen has 8. So 2, 4, 6, 8, 4, 6, 8. Now we combine them. So we're going to get 2 here, 2 here, 2 here, 2 here. Next up, let's fill in the lowest one first. So that took up 4. That leaves us with 4 more. And that is going to look something like that. Okay, so for our number of bonding, we have 2, 4, 6, 8, 10. For our number of antibonding, we have 2, 4, 6. So our bond order would be 10 minus 6 over 2. That's 4 over 2, and that is going to give us 2. So the higher the bond order equals the shorter the bond length. And if the bond length is shorter, that means they're closer together, which means there are more repulsive forces and just internuclear forces. And so we have a higher bond energy. And a really good way to just quickly gauge what your answer should be, you will have some scenarios where you do get a fraction, which you typically aren't presented with at the high school level. But in the case of oxygen, when we combine it, we get a double bond in between them and 2 electrons on each. That bond order of 2 is telling us that it's a double bond. If it was a bond order of 3, it would be a triple bond. So for example, this case, if we did the calculation, you get a bond order of 3. And that's about it for this question. Okay, next up, we would like the Lewis dot structure for propane. And so you can quickly look at this and tell that it's an alkane. Alkane should have the general formula CnH2n plus 2. If n is equal to 3, this is satisfied with C3H8. So we can already tell that this is going to be our saturated hydrocarbon. So let's just put down those 3C and the 8 hydrogens around it. And it should be completely saturated, which means single bonds, 2 hydrogen all around. The carbon seems satisfied with 4 bonds on each. Each hydrogen is satisfied with 1 bond on each. If you'd like to double check that you've done it correctly, you can again calculate the valence electrons and see if they've all been taken up. So we have 4 coming from carbon, but we have 3 carbons, plus 1 coming from hydrogen, but we have 8. And so that's just going to be 12 plus 8, which is 20. And you can just double check 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Meaning everything is satisfied. Okay, next up we're going to be using the periodic table to find the full electron configuration of barium. So you can use the Madelung's rule, which is illustrated below here, but it's just to let you know how it works. It just means that if you're filling orbitals, you fill it using the arrows. So in this case, we would fill 1s2 first, and then 2s2, and then 2p6, and then 3s2, and then 3p6, 4s2, 3d10, so on and so forth. The great thing is that the periodic table summarizes a lot of properties of the elements, so let's just pull it up. And so if you read the periodic table, you should read this as 1s for this first row, 2s, 2p, 3s, 3p. So, for example, in the case where we want the electronic configuration of carbon, you just read until you hit the carbon. So it's going to be 1s2, 2s2, 2p1, sorry, 2p2, and then that's carbon. And so it gets more complex as you come down here. Let me just draw it out. We're going to have a whole D group here. So here, this is going to be 1s, 1s, 2s, 3s, 2p, 3p. And once you hit the fourth group, here's where you see something interesting. You're going to have 4s here, and then you drop the number to represent this 3d that you're seeing right after. So 3d, and then back to 4p. And then again, something interesting happens when you hit the fifth group. So let's come back here, 5s, we go into 4d, 5p, and then once you hit the sixth group, you hit something called the lanthanides that are responsible for a different orbital group called the F group. And so you're going to have 5p immediately followed by 4f, and then 5d. And so it's what you see here, where you get into 5f, 5d, sorry, 4f, because you dropped the number by 2, 5d, and then back to 6p, and so on and so forth. So for our question, we would like to find barium, which is right here, thankfully, before we hit the lanthanides and get into the F situation. And so the yeah, and so actually bring it on this side. And so in the case we'd like to get to barium, let's first write the shorthand electronic configuration. And so barium is here. The closest noble gas is xenon. So it's going to be xenon and then 6s to get 6s2 to get to barium before we hit the lanthanides and get into the Fs. And so we have xenon and then 6s2 is the shorthand. If you'd like to write out the actual entire thing, you just read down the periodic table. And so we're going to have 1s2 for the first row, 2s2, 2p6, so by now I've reached here, 3s2, 3p6, 4s2, 3d10, because now we're going to start to see this D group here, and then back to 4p6, 5s2, 4d10, 5p6. So all of this is what we summarized by just writing xenon, and then lastly 6s2. And that's going to be our final answer. Okay, next up, we'd like to draw the Lewis structure of OF2 with O as our central atom. Let's just write that out. Again, we need to remember valence electrons. O contributes 6, and there's only 1. F contributes 7, and there's 2. So that's going to be 14 plus 6, which is going to give us 20. We know that oxygen is optimized for 2 bonds, and F is optimized for 1. So let's try giving that. And we see that both seem to be settled that way. Let's see if we can fit in all of the remaining valence electrons. For full octets, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Everything is satisfied. So this becomes our final structure. Okay, so we would like to find the possible Lewis structure for an isomer with the molecular formula C3H8O. So it would be tempting to assume that because the O is at the end, it would be a ketone or an aldehyde. But first, let's check if what the index of hydrogen deficiency is. And that's going to be 2C plus 2 minus the number of N minus the number of H minus any halogens we have over 2. So in the case of C3H8O, C is 3, H is 8. Oxygen isn't mentioned in this formula, so we don't include it. So 2 by 3 plus 2 minus 8 over 2. 6 plus 2 minus 8 is equal to 0. So this just becomes 0. So clearly all of the bonds to carbon are saturated, which means that this can't be a ketone or an aldehyde because that would violate that, because it would imply a double bond to oxygen at some point. And so let's try the theorized structure of a simple alcohol and see if the valence electrons permit for it. And so let's saturate it. And lastly, we have OH. Trying all of those bonds. Okay, and check our valence electrons. And we're going to have 4 by 3 plus 8 by 1 plus 6, which is going to give us 12 plus 8 plus 6, which is 26. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we have 4 electrons right here. It would be best to put them on oxygen because its octet isn't full yet. And everything else seems to be perfectly fine. Nothing that doesn't need to have one has an expanded octet, which means that this is our final structure. Okay, next up we have a calculation question. We need to find out what mass of solid NaCH3CO2 with a molar mass of 82 grams per mole should be added to 1 liter of 0.5 molar CH3CO2H to make a buffer with pH 4.21 if the Ka of CH3CO2H is 1.8 times 10 to the negative 5. And so for this question, we'll be using the Henderson-Hasselbalch equation. And that simply states that the pH is equal to the pKa plus the concentration of salt over, the logarithm of the concentration of salt over the concentration of acid. Okay, so clearly we are involved here, and we know that the concentration of salt would be completely dependent on how much of this is added because of the dissolution of it. So what is happening here is, the moles of the salts is going to be the mass, which we are trying to find, over the MR. So that's going to be X over 82 grams per mole. The moles of the acid is simply going to be 0.5 molar multiplied by 1.0 liter, and that's just going to be 0.5 moles. So if we rewrite the equation, we have the pH, 4.21. Oh, lastly, we need to calculate pKa. pKa is equal to the negative log of Ka, and that's going to be the negative logarithm of 1.8 times 10 to the negative 5. And that's going to give us 4.745. So our equation is going to look like this. 4.21, the pH given in the question, is equal to 4.745 plus log x over 82 divided by 0.5. And so now we just need to isolate x. Let's just So now let's isolate x. So first we're going to subtract this. So 4.21 minus 4.745 is equal to the logarithm of x over 82 over 0.5. I'm going to use the exponent notation to rewrite this. And it becomes 10 to the power of 4.21 minus 4.745 is equal to x. And we can just rewrite this as 82 times 0.5. And then we just drop that over here. So 82 grams per mole, this is unitless, times 0.5 moles, so these two cancel, times 10 to the power of 4.21 minus 4.745 is equal to x. And this is going to give us a final answer of 11.96 grams is equal to x. So you need to add 11.96 grams of this solid in order to make a buffer with a pH of 4.21, given all of these conditions. So for our next question, we'll be answering whether freezing is endothermic or it's exothermic. So first you need to understand what these two words mean and what freezing is. So first let's look at freezing. And you know that this is taking something from a liquid phase to a solid phase. And if we'd like to visualize that, we know that in the liquid phase, they're a bit further apart and have more kinetic energy and aren't as rigid. To the solid phase where they're practically fixed in position, so the kinetic energy is much lower, they're much more rigid, and so on and so forth. And so we're going from a state of high kinetic energy to low kinetic energy. And the kinetic energy that is missing can only be going in one place, and that is outside of the system itself. And so now we need to think about what endothermic means and what exothermic means. So for endothermic, energy is flowing into the system. This is how things get hotter. So for example, when you wash your hands with hot water, you feel the heat because heat is flowing into your hands, quite literally. So this should be, for example, the process where you boil water too, and you add energy, causing it to eventually vaporize. And exothermic is the opposite. Energy is flowing out. Now, we already described that in this case, it's going from high kinetic energy to low kinetic energy, and that the energy can only be going one place, outside of the system, which clearly means that the process is exothermic. It's losing energy to its surroundings. So the final answer is that freezing is an exothermic process. Okay, next up, we would like to find the molar mass of sodium sulfate and find out how many moles a sample of 300 grams represents. So the molar mass is just the sum of the number of a specific atom times the atomic mass of that atom it's just going to be the summation of that. So if we look at Na2SO4, we have 2 sodium, 1 sulfur, and 4 oxygen, and we need to look at the atomic mass of each. So for sodium, we have 22.99 grams per mole. For sulfur, we have 32.06 grams per mole. And lastly, for oxygen, we have 16.00 grams per mole. So if we want to find the molar mass, it is going to be equal to 2 by 22.99 plus 1 by 32.06, and this is all in grams per mole, plus 4 by 16.00, and that is going to give us an answer of 142.04 grams per mole. This is going to be molar mass of sodium sulfate. Next up, if we want to find how many moles are represented by 300 grams, we need to remember that moles is equal to mass over MR. There's unit consistency in this case, so we have a mass of 300 grams over an MR of 142.04 grams per mole. The grams cancel and the mole comes to the top. And this is going to give us 2.112 moles. And those are two answers. Okay, next up we want the molar mass of ammonia. We're just going to use the same formula up here. And just do the sum of the number of atoms multiplied by the atomic mass of atom. And so ammonia is NH3. So we have 3H and 1N. The atomic mass of hydrogen is going to be 1.00784 grams per mole. The atomic mass of nitrogen is going to be 14.0067 grams per mole. Please note all of these values can be found on the periodic table. Not this version, but it would usually be the number at the bottom. And so the molar mass is going to be 3 by 1.00784 grams per mole plus 1 by 14.0067 grams per mole. And this is going to give us 17.0302 grams. Oh, that's maybe our final answer. Okay, now for our final question. We'd like to find out the Lewis structure of NO2 minus. And so first let's count out those valence electrons. And please note that the charge adds 1. Okay, so N will provide 5 electrons. Oxygen is going to provide 6 electrons, but there are 2. And the charge will provide 1. So that is going to be 5 plus 12 plus 1, which is going to be 18 electrons that you need to take care of. And we know nitrogen is optimized for 3 bonds, oxygen is optimized for 2. So let's just write that out. And so let's start with the 2 bonds. But we see in this case, nitrogen isn't going to be happy, which means we will have to add 1 bond on one side. So one oxygen is going to be happy, while the other one is not going to be happy. By not happy, I just mean it's going to be responsible for that charge that you see. And now let's just add on electrons to fill each of their octets. So 2, 4, 6, 8, 2, 2, 4, 6, 8, 2, 4, 6, 8. And so let's just check. We know that they're 18, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14, 16, 18. Everything is satisfied. And because of the fact that this has can be on any of the two. Let's just draw the resonance structure, which is just the same thing, but now it's on the opposite side. And you can just leave the minus up there. And that's going to be our last question for today. Okay, that is all that I have for you today. I hope you enjoyed today's Q&A. If you would like to be informed of any upcoming videos, be sure to subscribe and also hit the bell button right next to it. If you would like to post questions of your own, be sure to visit the links in the description so you can be able to access OneClass. Be sure to like, comment, and share with your peers. This has been Marlyn from OneClass, and I hope to see you next time.